Yeah, we can get started. Thank you to everybody joining online and here in person. We're pleased to welcome Rae Holcomb, who's a fifth-year graduate student at the University of California, Irvine. She's working on building a data pipeline and commissioning software as a graduate shadow with the Pandora mission. And she was a predoctoral fellow at the Flatiron Institute in 2022. And I'll let her tell us about stellar rotation in the TESS era. Thanks.
Thank you so much for that introduction, and thank you everyone for being here in person and on Zoom. So let's get started. So first of all, hi, I'm Rae. As Allison said, I am a fifth-year grad student at University of California, Irvine. I'm based out here at Goddard for about 2 months while I work on some Pandora software. So I really would like to say, if you're in the area and you want to meet me and talk about anything related to TESS or any of the other topics I cover, I would absolutely love to sit down, say hi to people. Being a fifth year, I'm thinking about postdocs in the near future, so I love talking to people about research and other things. So what do I work on? I've really jumped projects between a lot of related fields as they pertain to stellar sciences and exoplanet sciences. Today I'm going to talk to you mostly about the first one, stellar rotation with TESS, but I also do a lot of work understanding M-dwarf activity, especially as it pertains to RV exoplanet surveys. I've done a lot of observing with both KPF and on Keck and with the HPF surveys. And then I also right now am working on Pandora. So kind of the through line here is I do a lot of things about how stars affect exoplanets and recover them. I'm not going to talk too much about the M-dwarfs or about Pandora today, but would love to in the future. You can always track me down to talk about that. I'm especially not going to talk about the RVs much, but I did want to throw up this one figure. I do scientific illustrations sometimes, and this is a figure that I made for a recent planet discovery paper, or more accurately, a planet characterization paper on TOI 1136. This is a super cool system. It's got 6, possibly 7 exoplanets where all 6 are transiting, and they're all in a very tightly packed resonant orbit around their young G-type star. So when we put the paper together, we were like, this system is too awesome to just let it be another planet paper on the pile. So my collaborator Corey Beard and Corey led the paper, asked me to create this visual to help explain to everyone just how awesome it is when you have all your ducks in a row. So I would like to show this because I think science can be a little bit fun, and I think this is a really cool system that we want to get more eyes on. But enough about that. Let's talk about what we're going to talk about today. So like I said, I'm going to focus talking about stellar rotation in the TESS era. I'm going to start by grounding what the history of this subfield looks like, talking about why we're interested in stellar rotation and how we've done it in the past. I'm going to talk about some of my present work, which focuses on a stellar rotation pipeline and catalog called SpinSpotter. And then I'm going to talk about a future project I have coming up called the TESS Rotation Collaboration. Jumping right to it, to the past. Let's talk about the history and motivation for stellar rotation studies. And I always like to start with this quote right here, which you may have seen before. It goes like this. Fred Hoyle once started a talk by saying, oh, basically a star is a pretty simple thing. And from the back of the room was heard the voice of R.O. Redmond saying, well, Fred, you look pretty simple too from 10 parsecs. I love this because it really encourages us to look deeper. As astronomers, we like to find the simple power law that explains the relationship. We like to find the hydrostatic equilibrium model where we can capture everything in just a few stellar equations. But the better our telescopes get and the deeper our understanding of all parts of astronomy, the more we realize that it's really in the things that don't quite line up. It's in the details and the complexities where we find the new interesting science. So why should you care about stellar rotation? Well, if you're a person who studies planets, stellar rotation has huge implications for stellar activity. Things like surface heterogeneity because of star spots. If you care about retrieving atmospheres, you really need to know what your star surface is doing. And if the star is spinning, that's going to affect it. It also has implications for habitability. For close-in planets around M-dwarfs, there are questions about what the magnetic environment could be like and how that could affect the magnetic environment of the planet. And if your star is rotating, that's really going to affect what that looks like. If you're not a planet person, you're more into galaxies, awesome. Rotation is a tracer of stellar age. It enables galactic archaeology and gives us a whole new perspective to study young clusters and moving groups. And if you study the in-between, the stellar astrophysics, hopefully I don't have to convince you, because that's what we're going to talk about today. So One of the things I like to point out whenever I talk about stellar rotation is that of the fundamental parameters of a star, rotation is one of the few that we can get a direct measurement of. It's not like age, it's not like radius, it's not dependent on a model. We can look at the star, we can see the spots go around, and we can say that is a period associated with the movement of the star. Now, obviously, there's some complexity to that. There's questions of differential rotation and rotation at different depths. Fundamentally, we can look at it and know the parameter. And this has some really interesting ties into the history and the evolution of the star. The beginning of this kind of all started in 1972. There was a paper by Skumanich et al., which described an age spin-down relationship for main sequence stars, mostly solar-like, FGK. And basically it showed that young stars have a wide distribution of stellar rotation, of rotation period. But as they evolve onto the main sequence, they converge into this really nice spin-down law. And so the thought was, if you can measure a bunch of stars and, measure the rotation periods of a bunch of stars, you can date them using their rotation. This birthed a field known as gyrochronology, where we look at stars that are in a single stellar cluster, so we know they have a common source, a common age. We look at their distribution of period over effective temperature, and we draw these isochrones that we can then use to describe how the rotation period of the cluster evolved over time as we look at older and older clusters. Gyrochronology has come leaps and bounds. There are still a lot of unanswered mysteries. We are very, very new to understanding what happens for cooler, smaller stars. And we have a lot of gaps. We have a lot of these age ranges where we don't have any known clusters. So we need more rotating stars. We need to know the provenance of more rotating stars. And, just the general astronomer problem of, we need more data, let's go and find some more. So how do we do this? How do we get our rotators? Historically, there were a couple methods. One of the first ones that was used a lot was spectroscopic line broadening, which I'm not going to go into the physics of too much, but when you have a faster rotating star, because of the Doppler shift on the two hemispheres moving towards and away from you, it broadens the spectral lines. This is difficult to scale up. On one hand, it is model dependent. You need to know what your base model for the star is. There's also multiple things that can broaden spectral lines, such as Zeeman broadening. And it's hard to do for a lot of stars. Spectroscopy is just more resource intensive than something like photometry. Yes. And it's also important to note that measuring stellar rotation, oops, sorry, did I skip a slide? Nope, okay. The other way that we can do this is we can look at the photometry of the star. When a star has spots on its surface, as the star rotates, those spots will move into and out of view of the line of the observer. And when the spot is facing you, the entire surface of the star will look a little bit dimmer. And so you can see these quasi-periodic brightness fluctuations over time. Now, this is awesome. You just need a photometer. It's less resource intensive than getting spectroscopy, and it's not model dependent. But it comes with some other challenges. Particularly, your star needs to have spots, which not all stars have spots all the time. And the fact that the shape of the periodicity can change, that it's quasi-periodic, can make retrieval a little bit more complicated. But it does open up a whole new era. Once we start getting wide field surveys, we get, actually before Kepler even, Spitzer was doing some rotation periods. Kepler was really what cracked it wide open though. Suddenly we're looking at tens of thousands, hundreds of thousands of stars. We're getting these nice, high precision, high cadence, long baseline observations. And suddenly we can just kind of get tons of these things. And, Kepler sort of opened this for the first time, looking at one particular part of the sky. TESS is taking that global, looking at more of the sky. And Plato in the future is going to continue this. And other upcoming wide field photometers are going to keep adding to the data we have to work on this. Kepler, like I said, was kind of the first one that cracked this open. For the first time, we went from having a few thousand stars with measured rotation periods that were all from different ground-based surveys, different methods, to suddenly we have this large statistical sample that's all coming from the same source. In 2014, McQuillan et al. Published a paper that published 34,000 rotation periods, and this is what their distribution looked like. And you can start to see these broad population features within the gyrochrone, within the period mass space. So I like to call this the isochrone swoop. It kind of looks like the same shape as those isochrones I showed earlier on the slide. And you can see there's kind of this upper envelope that older stars tend to pile up at. There's this intermediate period gap right here, which for a long time people were like, is that real? Is that some sort of bias in our sample? The more we look at it, the more we think that's a real astrophysical phenomenon that is hinting at, kind of a little snag in rotation evolution and how stars spin down across their lifetime. And what's cool, if this loads, is we can look at the shape of this distribution over time and actually see how stars evolve in rotation space as they age. So this is a figure from Ruth Angus, and I'm going to play it once, and then I'm going to play it again and narrate it. So what's going to happen is we're looking at our plot. Ooh, if it loads, cross your fingers, guys. There we go. And we're moving from younger stars to older stars. So watch that for a second. So we start with our young stars, which start as faster rotators, and as they age, they spin down. Ooh, I'll play it again. As they age, they spin down and then slowly pile up at this upper envelope. And you can see, if you pay attention to this right side, you can see when they all kind of leap across the gap. There's sort of an age of ranges where they're split across, and individual stars will leap across the gap quickly, which I guess you wouldn't actually see the individual stars do that because we're looking at a moment in time. But it's awesome that we can take the statistical sample and actually see the evolution of our population as time goes on. All right, so my answer to this is that's awesome. We still got things to solve. Let's get more data. And this is when TESS comes in. I'm guessing a lot of you guys are going to be pretty familiar with TESS on this call, so I'm going to do a little less background than I normally do. But stop me if there's anything you don't know. So the Transient Exoplanet Survey satellite is doing photometric monitoring of essentially the entire sky, 90% of the sky, and it's doing it at high cadence across shorter sectors than Kepler. So we're only looking for 28 days at each patch of the sky, but we are looking at the entire sky as opposed to Kepler's strategy of looking at one part of the sky. This means that we're going to get a whole lot more field stars distributed across the sky, but that also means across the galaxy. We're going to be probing different parts of the Milky Way and our nearby solar neighborhood. But with this awesome new data set comes a number of new challenges. That short baseline I mentioned of only having 28 days looking at one part of the sky makes certain things really hard, especially when you're looking for slow rotators. There's also a lot of systematics to deal with, and the pipeline products are really optimized for finding planetary transits. Stellar rotation is kind of a secondary thing that people have figured out how to do with TESS. And so because of that, the detrending used in a lot of the pipeline products can squash out your longer-term signals. And TESS has pretty large pixels, which means you're always running a risk of being contaminated by neighbors, and you really have to keep an eye out for that. So the upshot is a wealth of data provides both an opportunity and a challenge, and quite frankly, far more light curves than any grad student wants to sit through and look at one by one. So the question becomes, how can we intelligently and effectively automate the process of looking for our stellar rotation periods? That brings us to part 2, the present. So, like I said, there's more TESS stars than any grad student wants to look through, underpaid as we are. But even I sit down and I look at 200,000 2-minute cadence stars, and I say, surely there's a way to get the computer to do this for me. And so that's what I did. I created a fast automated algorithm that searches through high cadence photometry, designed on TESS, but it works on other surveys too, in order to recover stellar rotation periods. It actually started as an undergraduate project for my senior thesis, and I've sort of carried it with me, and it's evolved over the years as I've worked on it. So what is a spin spotter? Number one, it is designed to be fast, automated, open source, and it's based on autocorrelation, which I'll talk about more in a second. It's designed to scale up well for large photometric data sets, and it's designed to be relatively flexible, so you can kind of adjust it to your science case. The fundamental statistic that it's relying on is the autocorrelation function, which measures self-similarity in a function at different lags. So you can imagine you take the function, you take a copy of itself, and you slide it along, and at each offset, you measure how well does the function correlate with itself. So if you have a strong periodicity, you'll see repeated peaks at integer multiples of that periodicity. How does that translate to stellar rotation? I would like to show you some of the data and show you what a good, rotation period looks like and what a bad one looks like. So these are two quote-unquote good examples. On the left, we have a classic single dipper rotator. Look at that beautiful repeated peak. It's gorgeous. It makes my heart sing. I love that. I wish all stars looked like that, but they do not. On the right-hand side, we have another rotating star that's a little bit messier. This is a common complication that we run into that happens when you have spots on opposite hemispheres. And so you get a partial correlation at half the period. You have to be a little bit careful that you don't pick up the half-period aliases. Then there's also the question, what does a rotator not look like? One of our common false positives is eclipsing binaries, especially grazing eclipsing binaries. The closer you are, the more it can kind of smooth out and sort of look like rotation. But they do tend to have larger amplitudes in their transits, and also they kind of look spiky. They tend not to be as smoothly evolving as rotators, although that's not strictly true. And then, of course, you can have non-rotators, where it's just kind of noise and there's no real strong correlation. Sometimes you can look at these and kind of fool yourself into thinking you're seeing something, but resist that urge. So the way SpinSpotter does this, we take our TESS light curve, which is on top, we calculate the autocorrelation function, and then we need to find those repeated peaks. And the way I chose to do this was building on a method by Saylor et al. 2017, where rather than just using a naive peak finding algorithm, we actually fit parabolas to the autocorrelation function. And the motivation for this is to really probe the shape of the peaks. We want to know, are we just getting a single spike that's coming up, something that might be caused by a transit event, or are we getting this nice smoothly varying peak? And having the parabola lets us look at that. We can characterize the height of the peak, we can characterize the width of it at the zero crossing, and the fit. So that way we can say, okay, our peaks are kind of peak-shaped. And then what this does is we can tune our cutoff parameters to retrieve autocorrelation functions that are shaped the way we want. So we put constraints on how tall the peak needs to be for detection significance, how wide they are to make sure they're not too broad or too spiky, and making sure that our parabolas are actually fitting it well and reporting what we think they're reporting. I also report a few other descriptive parameters that we don't make cuts on, but which are useful for vetting. I won't go too into those. These are light curve descriptive statistics rather than autocorrelation function descriptive. But you can see when we calculate all these summary statistics and we plot them out, we can see we actually do a really good job separating the rotators from the non-rotators. The way I made these plots is I sat through and I hand tagged a couple thousand rotators by hand to basically build up my own training set. And then I split it in half, actually into 1/3 and 2/3. And I tuned my cutoffs based off of one of them and then saw how the retrieval went on the testing set. Blues are rotators, turquoise are ones that were tagged as possibly rotation but needed more verification, and purple are non-rotators. And you can see in the space of these descriptive parameters, the rotators pop out quite nicely overall. And you can also look at this if you care more about completion, if you can kind of prioritize whether you want to really damp down on the false positives and have a very exclusive cut, or if you're like, we want to catch everything that might be a rotator, but be willing to accept more false positives, you can kind of move these lines around and get a sense of what you're getting. So what does my sample look like? This is my big summary plot from the paper. I call this the salmon plot because one of my collaborators pointed out it looked like a leaking salmon, which I think is hilarious. The pink points are from McQuillan et al., so those are rotators from the Kepler sample. The blue points are from SpinSpotter. I recovered about 13,000 periods, which is about a 10% yield, which is fairly consistent with what we've seen from other test rotation catalogs. And we see a couple really interesting features pop out. First of all, we have this cutoff right around 10 days. And this is going to come up over and over again when you talk about stellar rotation with TESS. This is a limit imposed by the 28-day sector observing strategy. Basically, it's just hard to recover periods when you're only looking at the sky in chunks like this. It's hard to get periods that are more than about a third or half the baseline. We also see that there's this whole population of fast-rotating M dwarfs that Kepler didn't pick up. This has to do with both TESS's redder bandpass is better for M dwarfs, and also the way that the input catalogs were built for the two survey strategies for Kepler, it excluded a lot of these M dwarfs. So we're getting this whole new population of really interesting fast rotators that we've never really been able to study in detail before. And of course, we can take my results, we can hold them up next to previous studies and say, are these sensible? This is a comparison that I did to various young cluster catalogs, where you can see I compare my rotation periods to literature rotation periods for various young clusters and moving groups. And there is quite nice agreement, but you'll see it really does break down right around 10 days. This is saying as we approach that 1/3 of the baseline limit, we have to be a little more dubious about those rotation periods we're getting, make sure that we, we're kind of hitting our detection limit there. Additionally, Isabel Coleman, just last month, I'm so excited, I've been waiting for her paper for ages. She just published her own TESS rotation catalog, which you can find in Coleman et al. 2024, sorry, I wrote that wrong, it's 2024, not 2022. And she did a fantastic comparison of various published TESS rotation catalogs. I won't go into all of these, but things like the Santos catalog focused on TOIs. Clater et al., it was focused on recovering long rotators. Sorry, no, I think I might have gotten that backwards. I think Kukul et al. Focused on TOIs, and Santos was on young moving groups. My apologies. It's really interesting to compare the spin spotter and Isabel Coleman's tool is called Spinneret. The Spinneret sample, because we both performed our analyses on the 2-minute cadence light curve sample from TESS. And so our results are very comparable, but we used complementary methods. I used the autocorrelation function. She used a random forest classifier that was based on the 2-term Lomsgargle periodogram, which is very interesting. There's been a lot of discussion about whether autocorrelation or periodograms are better for stellar rotation recovery. The benefits of Lomsgargle being that it, you have to do less to, you don't have to have an evenly spaced time series, so it deals a little bit better with the gaps. But because it's Fourier-based, you kind of have to do a global fit of the shape of the periodicity. And so it's less robust against quasi-periodic signals that change. Whereas the autocorrelation function, it deals a lot better with that quasi-periodicity, but how do I put this into words? It can be a little wigglier in places where you don't want it to. It can be a little bit harder to wrangle into something that you can interpret statistically at times. But we do see common features between our catalogs. First of all, we see that all of the TESS catalogs that are based on the 2-minute cadence light curves have a sharp drop-off in detection around 10 days. Once again, we're showing over and over again, this is a result of the way that TESS light curves are collected and processed, more so than the recovery algorithms used, because we all use different algorithms. There's also a pervasive overdensity of periods between 5 and 7 days. And there's a lot of discussion about where this comes from, whether it's a systematic in the spacecraft. Coleman suggests that it may be an overdensity where we're seeing 12 to 13-day periods, but they're being picked up as half-period aliases. And in particular, when she does a comparison between our catalogs, on the left, we have a comparison between the period she recovered and the period I recovered before she does adjustments for half-period aliases, and then again after. And this just goes to show that half-period alias is very strong when you're looking at stellar rotation, and you have to do careful vetting to make sure that you're picking up the right one. Interestingly, we don't see very much at 1/3 aliases or other multiples. It really seems to drop off after the half-period alias. Let's see. It has to do with how she does her internal classifications from the random forest. I don't remember exactly what they corresponded to. Yeah, because she has a 2-step classification process, and I think the color is referring to what happened during the first step of classification. Now you might say, this is awesome, what can we use this for? And I'm like, well, all sorts of things. But what I've used it for so far, particularly for spin spotter, is that because it scales so well and it's quite fast, it's excellent for survey selection. If you are building up any sort of survey where you care about rotating stars or stellar activity, spin spotter is a great way to take a giant pile of targets and turn it into a list of which ones are rotating quickly and which ones are not. I've used this for the SURFSUP program, which is looking at ultra-fast rotating M-dwarfs with periods less than 5 days. I've used this to help with some metallicity follow-up surveys. And currently, I'm working with the team working on the GEM survey, which is searching for giant exoplanets around M-stars to help tune their target selection. And because SpinSpotter is flexible in what parameters it gets back to you, there's also the possibility to use it for other science cases. There's been some really interesting discussion about how to recover spot lifetimes from autocorrelation functions by looking at how quickly the height of the peaks decay. And SpinSpotter returns this metric, so you kind of get it for free. Now, this is also heavily affected by how your light curve is extracted and then cleaned, but there's opportunities to look at more than just the period. You can also explore other features of the stellar surface through SpinSpotter. So in summary, and I have to check how I'm doing on time. All right, we got about 10 more minutes. This is perfect. In summary, SpinSpotter is a fast, flexible, easy to use, and open source tool that you can use to look at rotation periods. You can also just get in contact with me, and I will send you the catalog if you want a giant list of rotating stars. It is a catalog of about 13,000 periods with rotation periods from 0.4 to 10 days. It can also retrieve faster rotators. That was just a cutoff that I put in my catalog when I was creating it. And I am still, adding new features and especially tuning it to do faster rotators better. So if you have any interest in any sort of large-scale stellar rotation measurements, definitely get in contact with me. Let's talk. Awesome. So that's what I've been doing. Now let's talk about what I'm planning to do. And I want to talk about the TESS rotation collaboration. And here's where I want to start. It really is a collaboration. This is a photograph taken from a conference that happened in 2022 called 50 Years of the Scumanich Relationship that celebrated the 50-year anniversary of that 1972 paper that kind of opened up the field of gyrochronology. And this was amazing. I went to this conference, and it was like 50 people all in a room who just care about how stars spin, and we just talked for a week and was like, holy crap, there's so much good science going on here. And this started a lot of really productive discussions that I think started a lot of productive discussions. Another aspect of this is also that TESS itself is really encouraging community collaboration. The fact that there's no proprietary periods, the fact that you go on the TESS website and there's literally a tab called Community Tools where you click on it, it tells you all the open source software that people have made and published. This is really an era where people are bringing the work they've done to the table and saying, how can we use each other's stuff? How can we help each other do better science? And I think the published science reflects this really well. If you go on ADS, there are dozens of tools to help get better science out of TESS. There's all sorts of FFI and light curve tools. This is just a selection. This is not exhaustive. But you have things like the Eleanor pipeline, Dax Felis's Nemesis pipeline, which also has some interesting features for looking at flares. There's the TGLC pipeline by another grad student in my group named Tae Han that is very promising for looking at longer period or longer baseline signals within TESS. And then if you look specifically at rotation pipelines and catalogs, there's also a ton. There's people who are looking specifically at slow rotators, such as Clader et al. And Hattori's unpopular pipeline. There's people looking at the TOYs, looking at rotation in clusters. There's my own tool, SpinSpotter, and then a variety of others, including Isabel Coleman's Spinneret. And what we see is people are attacking this problem from many different angles. We've got Fourier-based solutions like the Long-Scargle periodogram or the two-term Long-Scargle. People like me who are working with autocorrelation. There's also wavelet decomposition. Ruth Angus's group is doing some really interesting work using Gaussian processes to measure rotation periods. And then there's a whole suite of new machine learning tools, things like the random forest classifiers, things like Zachary Clader's long period rotator catalog as well. And this opens up a whole new realm of questions. We have all these great tools, but now we have to ask, okay, what's the right tool for the right job? How good are we actually at measuring rotation periods? What blind spots do we still have in our parameter space? What are the inherent limitations of TESS's survey strategy? Are there certain ceilings that we are bumping up against that we need to figure out how to get around, or that we might just not be able to get around because of how the survey is designed? And then if you are someone who's interested in using this for your science, which tool do you start with? There's so many awesome ones to choose from. So we need a way to sit down and compare notes. There is precedent for this. If you go back and you look at the Kepler survey, in 2015, Suzanne Agren ran a data challenge where she invited 5 different teams to recover rotation periods of simulated rotators that were injected into Kepler data. And this was awesome. It was kind of a sit down, and we're all going to look at which methods work well in different parts of parameter space. And so I read this paper and I said, this is awesome. We need this for TESS. And so that's what I'm doing. It's called the TESS Rotation Collaboration, and it is a collaborative effort to compare different rotation finding methods on simulated TESS data. The goals here are threefold. We want to provide a standardized framework to understand what methods work well in different parts of parameter space. We want to evaluate the field's overall current ability to measure stellar rotation and how confident we are in the rotation periods we recover. And we want to aim to be a user guide for people who are outside the field and want to use our tools. It can be a little overwhelming to step into a new subfield and, process the dozens of papers on this topic. And so this can help get people to the tools that will help their science most more quickly. It's a 5-step program, if you will. Step 1 was to reach out and see if there was community interest. This is something that I've already done. I started the process in late 2022. Basically just talked to people I knew, sent out a lot of cold emails and said, hey, I want to run this data challenge. Would you be interested in contributing some analysis? And the response I got was overwhelmingly positive. So many people said, yeah, this sounds really awesome. A number of people said, I've literally thought about doing this myself, but I don't have time, so I'm glad somebody is doing it. And just generally making sure that this was a need that the community had that I could serve. Step 2 is to generate the data set. I can talk about more about that in a second. But basically doing the injection of the rotations into simulated TESS data. That's what I'm working on right now. We're getting very close to having good data products, but we got to do a little more testing. We got to scale it up a little bit. Once we pass that point, we'll be distributing the data to the teams and giving them a few months to run their rotation pipelines on the data. And they'll send their results back to me. I'll do a meta-analysis. We'll take a look at what everybody found, and then writing and publication, which I will also be leading. I will say I have this little We Are Here. We have been at We Are Here for about a year now. Since I started working on Pandora, this project has been put on hold for a little bit, but it is still underway, and I'm still very excited to get it moving again once the schedules line up a little bit more. So what's the data that we're going to be using? It was important when thinking about this, we want to capture as many of the TESS systematics as possible. So because of this, we're actually going back and injecting our simulated light curves into the 2D pixel images. We're actually pulling cutouts of full frame images, using the TESS point spread function to smear out our 1D light curves into 2D, add them in there, and then re-extracting them using basic photometry pipeline. We're going to provide both the FFI cutouts and the 1D light curves to our users. This is because different people's pipelines are designed to run on different data products, and we want to mimic the TESS data products as well as possible. This will also help us figure out just how much extraction pipeline, the PSS pipeline, matters when you're trying to recover these rotation signals. Currently aiming for the data set, sorry, I think my microphone is getting, sorry about that. Currently aiming for the data set to contain about 1,000 stars, but with a core set of 1,000. So if you're not set up to run quite such a big data set, you can run the smaller one and still participate in the data challenge. For the analysis, we're interested in several things. First, for each team, we want to look at what their yield was. How many of the injected rotation periods did they manage to extract out correctly? What their accuracy is, what their ratio of false positives to true positives was. And then we also want to look at this in context of how long the rotation period is. Extracting fast rotators and slow rotators from TESS is a very different problem, and we want to see which methods succeed in different parts of parameter space. And then there will also be some report of the computational resources needed. Some algorithms run fine on a laptop, others need a supercomputer, and we want to keep that in mind when we're thinking about what the use cases for all these tools are. Then, as a population, we want to look at the difference about whether people started with the FFI or the light curve object get a sense of how much that light curve extraction part of the process affects what your final product is. We want to compare different method types for periodograms, autocorrelation, machine learning, et cetera. We want to see how multi-sector treatment affects your retrievals. This is something I didn't talk about a lot, but how you stitch your test sectors together really affects what your upper limit of periods you can find is. And we want to figure out which methods work well, who's actually doing this, and what's the return on that. And then we also want to know what our susceptibility to various types of aliases are. So that way, when you see a rotation period in the light curve, how much can you be like, that's definitely the rotation period, or maybe we should keep in mind that the rotation period could actually be twice that number. The key questions we aim to answer is what methods provide the highest accuracy and the highest yield? How accessible are the different methods? We want to really highlight things that are open source and available to the community. We want to answer the question about whether it's better to start with the SSIs or with the light curves, and how that part of the processing works. We want to look at slow versus medium versus fast rotators and understand how to treat each of these populations effectively. And then we kind of want to summarize, as a field, how are we doing? How much can we actually say we know the rotation periods of these stars, and how can we get more? I also want to highlight who's involved. These are the logos of everyone who's provisionally said, yes, I want to contribute analysis to this. Obviously, these things move around and change as schedules change, but I think it's just really a testament to the fact that this is a need in the community that people are really interested in seeing solved. There's been some fantastic response and involvement. And if you want to get involved, feel free to send me an email or scan this QR code. It'll also be up on my question slide at the end. If you work on stellar rotation or you know someone who does, please reach out to me. I would love to talk to them. Since I'm still in the phase of getting all the data products ready, this is a fantastic time to come to me and say, I want to participate. My pipeline works like this. That way I can know how to accommodate everyone and make it easy for people to participate. And that's the summary. So I want to say thank you, everyone, for listening. I've got a link to SpinSpotter if you're curious in using my rotation period measuring tool. Also, I don't have the QR code. You can email me, or I can go back a slide if people want to see the QR code again. Yeah. But thank you for listening, and I would love to take some questions.
Hello? Okay, great. Yeah, thank you so much for a great talk, Rae. If there are people online with questions, feel free to chime in or put them in the chat. Or anybody here?
Awesome talk. I was curious, when you were, I think this project that you're working on now is really great, and I'm excited to see what comes out of it. But I'm not familiar with that kind of precursor one that was done with Kepler. What sort of things came out of that in terms of, did we find that certain tools were better for certain parameter spaces? Like, what lessons have we learned from this study that you're applying now for this new one?
Yeah, so we learned, okay, got my thoughts in order. One of the interesting things that came out of this was they actually learned that they made the retrievals too easy. So all of the methods had a pretty high yield. A lot of them got 90+% of the rotators with pretty good accuracy. And part of that was because there was not nearly as much injection of things that were like false positives. There were also, this study did not include non-rotators. It didn't have any non-rotators in the sample. So it was just, can you get the correct rotation period for stars that are definitely rotating? So we're definitely structuring the sample a little bit more to basically provide more realistic ways to trip up pipelines. But it did illuminate some of the strengths and weaknesses of Lom's-Gargle periodograms, autocorrelation function, and wavelet decomposition. One of the things they found was that combined methods that used multiple approaches and then kind of consolidated the answers from all of them tended to do better, which I think goes to show that each of these methods has their own strengths and weaknesses. And if you can tease out what those strengths are, you can improve the population retrieval.
I had a question. So going back to this kind of like 10-day rotation period kind of wall that you're hitting, You mentioned towards the end, like multi-sector treatments. So you haven't done that, and that would be a way to like get past this 10-day.
I actually have done multi-sector treatment. SpinSpotter runs its algorithm on each sector individually and then on a combined stitched one to, first of all, see if it can get at longer rotation periods, and then to validate between which one is correct. So sometimes you'll have multiple sectors and they'll give you slightly different answers, and the multi-sector will help you distinguish between them, especially if you're distinguishing between half-period aliases. So I actually did do sector stitching, and it did not help me beat this 10-day detection limit. And that is because I was using the PDC SAP light curves, and those are very heavily detrended on timescales of about a sector. And so that's really an inherent limitation to that particular pipeline extraction. And that's something that's come up in my study. It's come up in other studies that have looked at the PDC light curve. There's a lot of hope that other light curves, I've seen people use Eleanor. I know TGLC is very promising. There's a lot of hope that these other methods of doing photometry extraction can help preserve those longer-term signals. But I haven't had a chance to run SpinSpotter on those yet.
Yeah, so the kind of like pronounced bump you have here at 10 days compared to the other kind of samples, that I guess I'm wondering why the other sample sort of doesn't hit that wall so sharply, if that makes sense.
Yeah, Coleman 2024 does have it some, and then they do some adjustments for the half-period alias that smooths it out to a certain extent. I think it's because they have a more sophisticated approach to identifying the half-period alias than I do. I have a very simple, like, how tall are the peaks, and are they different enough by enough? So I explain in my paper this overdensity as a reflection effect of this population, this overdensity of 5 to 7 day periods that's kind of getting reflected up into this longer period space. Yeah, and so in order to deal with that, you would have to have basically a better way to distinguish between the half period and the full period alias, which is also something that could absolutely be helped with better sector stitching.
Cool, interesting. Yeah, we have a question online from Tom Barclay. I have a question about Roman. Have you thought at all about what we could do for Roman in the galactic bulge? One possible thought could be using your data challenge framework for a Roman data challenge.
That's a super interesting idea. I'm not very familiar with Roman as a mission. I actually learned a whole lot about it at the Seek Symposium lately, and that's the most that I've like heard about it in one sitting. So I'm also super interested in that question. I'm not very equipped to run this kind of data set challenge for Roman because I'm not as familiar with the instrument parameters, and really no one is because it's not fully built yet. You know, we'll know what the systematics are better when we have a system. I would love to see something like that. One of the big challenges in the galactic bulge is going to be neighbor contamination and crowding. Roman has much better resolution, but you're still going to have that issue just because the galactic bulge is very, very populated. So I would love to see someone do that, but I'm probably not the right person for it. Maybe collaborating with someone who knows Roman. Talk to me.
You mean you're not going to fix everything for us?
I mean, I would love to, but they have to pay me more to do that.
Any other questions here or online? Not seeing one. I guess I had another question about your salmon plot,
yes,
which I like that. I like the coloring and the name. Yeah, so for these, going back to this 10-day kind of wall, do you have a sense of if these populations would spread out smoothly from there, or like what, do you have a sense of like the underlying population? Yeah,
so once again, it's difficult because we're missing the kind of medium and longer term rotators. I think it's encouraging that when you look at the hotter stars, we follow the kind of isochrone swoop quite well, and then we sort of get ratty as we approach our detection limit. We don't go high enough to know whether we see the intermediate period gap or not, but people who have looked at specific stars in TESS keep pulling up evidence that supports it. And I also know there was analysis done on the K2 sample that also found the intermediate period gap, so it's not something that's just localized to the Kepler field. think I got off track your question a little bit.
Yeah, I guess like if you didn't have this sort of limitation, do you expect the population to kind of continue evolving smoothly past that 10 days?
Yes, I would expect that. Obviously, I don't have the data to support it, but TESS is picking up a lot more field stars, and it would be interesting because the global population of TESS and the global population of Kepler are going to be a little different because of the sky distribution. But on the whole, I think people are finding results that are consistent with Kepler and consistent with our understanding of main sequence spin down. The M dwarfs are really the big new population. Everyone's like, ooh, new mechanisms. There's like discussion of stalled spin down and braking, especially when you get to the fully convective regime. To go off on a tangent a little bit, a lot of the spin down braking happenings because of the boundary between the radiative zone and the convective outer envelope. And as you move to fully convective M dwarfs, you no longer have that boundary because you don't have a radiative core anymore. And so there's a lot of questions of how does this affect the spin down law. And indeed, we kind of seem to see, have this population of extremely fast rotators in M dwarfs that seem to not be spinning down properly, or some of them possibly seem to have gotten spun up by other processes. And so there's a lot of interest in what's governing these fully convective M dwarfs.
Yeah, so that overdensity is mostly fully convective ones, right?
Let's see, I think, where is the temperature cutoff for this? I always forget. I think it's actually a little bit cooler. These are not all fully convective. This, yeah, I don't remember where the number cutoff is, but the Kepler just didn't get cool enough to get to the fully convective ones. TESS does for some.